Hello, this is Mr. Buss. Welcome to Chapter 8, Polygons and Circles. Homework questions 6 through 12 on Lesson 8.1.1. Question 6. Solve for x in each diagram below. So on Part A, we're going to use the triangle angle sum theorem since we're missing the third side or the third angle of the triangle. So we know all three angles should add up to 180. So we can also just do 180 minus 75 minus 35 degrees. And that will give us 70 degrees for the third angle. So we'll mark that in there. That's 70 degrees. And then the exterior angle here, angle X, this is a straight angle. So now we can take 180 degrees and subtract the 70 degrees to get 110 degrees. So therefore X is equal to 110 degrees. And what you might recognize is that this exterior angle, because those two were adding up and taking 180 minus those two, we're also 110. Part B, kind of the same idea here, but we do recognize that maybe given a little less information, but these two sides are the same, which means these two angles opposite those are also the same. So that is x and x, and then this is a straight angle. So since 140, you're going to take 180 minus 140, and that will give you 40 degrees. And then therefore we know that x plus 40 degrees should equal 180, or 2x, subtract 40 is 140, x is equal to 70 degrees. On part C, we have 148 degrees, once again creating a straight angle, so we can take 180 degrees minus 148 degrees. And that will be 32 degrees. And so mark that in there. This is 32. And then once again, all three angles have to add up to 180 degrees by the triangle angle sum theorem. So we have 180 degrees is equal to 132 degrees plus x. Subtract 132. And we get x is equal to 48 degrees. In part D, we have these two angles that are equal to each other, so the opposite side lengths are equal to each other. If that's helpful, I guess we don't necessarily need that, but since we know these two are equal to each other, we can take 180 minus the 36 degrees, and so that would be 144 degrees. And since these two angles, once again, we can call them x or whatever you want to there, but they're the same, so we know that the sum of those two should equal 144 degrees. Divide by 2, and you get 72 degrees. Now, I shouldn't have actually called that x, since we already have the variable over here as x. So let me see if I can do a quick switch out here. Let's just go ahead and call that y. And so then 2y, and then y is equal to 72. And since we know that's 72, and there's your straight angle right there with x and y, then x plus 72 degrees should equal 180 degrees. Subtract 72 from 180, and that will give you 108 degrees for angle x. Question 7. Use the definition of polygons from the math notes box in this lesson. Determine whether each of the following figures is or is not a polygon. Justify your decisions for each figure. And if you go back to the math notes box, it was talking about convex and non-convex polygons, but the very first sentence, I'll read it to you. It says, a polygon is defined as a two-dimensional closed figure made up of straight line segments connected end to end. These segments may not cross or intersect any other points. So go back to your math notes and look at that again, but once again, that's the definition of a polygon, and we're going to use that to help us identify whether these are polygons or not. So the first one, A, would that be a polygon? And if you go back once again to the definition, it talks about straight line segments. So you can see this one right here has a curve. So this one is no, that it is not a polygon. B is a triangle, so yes, it does represent a polygon. That one looks good. C, this one is no, it does connect. There's no curves, but we have the part of where it says it cannot, line segments cannot intersect or cross each other. So C is out. D looks good. It is a non-convex polygon, but it's still a polygon, so that's okay. So B and D are okay, A and C are not. E, we run into actually a couple issues here. One, it intersects, and another one, you have these endpoints that don't connect back. So, nope, that one's not going to work. F is a star, everything's connected, looks good. G looks like a trapezoid, so that one looks good, everything is closed. H has all straight lines, but it doesn't connect here. So once again, there has to be that connection, and since there is not, that one will not work as well. Question 8. After solving for x in each of the diagrams in problem 8-6, Jerome thinks he sees a pattern. He notices that the measure of an exterior angle of a triangle is related to this two of the angles of a triangle, which if you watched question 6, kind of talked about that a little bit. Part A, do you see a pattern? To help find a pattern, study the results of problem 8-6. So going back, what you notice is, and we can kind of write this out, is we have angle A plus B plus C, that has to equal 180 degrees by the triangle angle sum theorem. But what we also have is that this exterior angle, x, plus C, also will equal 180 degrees. And so since you can see they both equal 180 degrees, we can substitute this expression, since it's equal to 180, in for that one. And so then we get A plus B plus C is equal to x plus c, and then you notice that the c's in common, so we're going to subtract c from both sides, and you're left with a plus b is equal to x. And so the sum of your remote interior angles here are equal to the exterior angle. So that's kind of the pattern that hopefully you were able to see for part A, that the measure of the exterior angle of a triangle equals the sum of the measure of its remote interior angles. So that kind of answers part A there. Part B, in the example at the right, it just kind of goes through and explains what we just talked about. A and B are called remote interior angles of the given exterior angle because they are not adjacent to the exterior angle. So that's why we know how something is a remote interior angle, because they're not adjacent to the exterior angle. So it really depends on what exterior angle you're looking at and what your remote interior angles are. Write a conjecture about the relationship between the remote interior and exterior angles of a triangle, which we kind of already said. Once again, the measure of the exterior angle of a triangle equals the sum of the measure of its remote interior angles. And then I'll write that out in a second. And then part C, prove that the conjecture you wrote for part B is true for all triangles. Your proof can be written in any form as long as it is convincing and provides reasons for all statements. Once again, I kind of already did that when we were talking about part A. Over here is that, you know, we set up these two equations based on information that we previously had. This is the triangle angle sum theorem. And this is our straight angle, because we know they're equal to 180, and then we use substitution, and then we subtracted C, and then we were left with our conjecture is that the remote interior angles, the sum of them, were equal to the exterior angle. So we can use that as our proof. It doesn't have to be a flowchart or a two-column proof, but this, it says, you know, as long as it's convincing and provides reasons for all of the statements. So I think we're good there as well. And so then I went ahead and kind of wrote a more formal answer for part B. That was the conjecture that we were trying to prove. And then once again over here is kind of how we prove that. Question 9, examine the geometric relationship in the diagram at the right. Show all steps in your solutions for x and y. So one of the things that was discovered hopefully today during your core lesson is that the circle creates an angle of 360 degrees, which is stuff that we've talked about before. But since all of these triangles have the same value, we know that there are, what, 3 of them or 5 of them? So we know that x plus x plus x plus x plus x, or 5x, has to equal the angle in terms of a circle. A full rotation is 360 degrees. So then we can divide by 5 and get an x value of 72 degrees. So we know the angle for all of those triangles is 72 degrees at x, and then the y, since it is an isosceles triangle, once again we know that x plus y is equal to 180 degrees, but we know x is 72 degrees already, so we can plug that in. Y plus y is 2y, subtract 72 degrees, that would be 108 degrees, divide by 2, and we get a y value of 54 degrees. So 72 degrees plus 54 degrees plus another 54 degrees should equal 180 degrees. Question 10. Stephen has 100 congruent triangles that each has an angle measuring 15 degrees. How many triangles would he need to use to make a pinwheel? Explain how you found your answer. So you're going to put all the 15-degree angles in the center. So therefore, you have, once again, 360 degrees makes that full rotation. And if you divide that by that 15 degrees that you're always putting in the center, you will get a total of 24 triangles that you will need to create that pinwheel. So 24 triangles total is what you would need, once again, to create the pinwheel. Thinking about that rotation, that circle where you're putting all the 15-degree angles. Question 11. Find the value of x in each of the diagram below. If possible, if the triangles are congruent, state which triangle congruency property was used. If the triangles are not congruent, or if there is not enough information, state cannot be determined. So in part A, we're looking for the value of x. We do know that the two lines here and here are parallel by the markings. So if this is 73 degrees, we know its alternate interior angle has to be the same. So that's 73 degrees as well down here. So what we have is we have this side 7, this side 7. This is the same side, so the reflexive property allows us to say that those are congruent. And then now we also know that 73 degrees and 73 degrees are congruent. So by side, angle, side, we know that the triangles are congruent, which means that their corresponding parts are congruent. So this 28 degrees is also this 28 degrees. And so now we can use the triangle angle sum theorem to say that all three angles have to add up to 180 degrees. So I'm going to take 180 minus 73 degrees minus 28 degrees, and then that will give us a value of 79 degrees. So x is equal to 79 degrees, and we also know that the triangles are congruent by side angle side congruency. For part B, we have an angle measure that is the same, so that's 23 degrees. We also have vertical angles, so we know that these two are congruent. And then we have this measure of 9, which looks like it's going to be helpful. But what you might notice is this 9 right here is not the same 9 in terms of where it's located in the triangle that it is right here. This one on this side is in between the two angles that were congruent. So this would be like angle side angle, where this one over here on this side is in the place where this would be angle angle side. So because of that, we don't have that congruency to say that x should equal 6. So on this one cannot be determined because we can't determine if the triangles actually are congruent, really because of where that 9 is located. It's not right in the right spot for those triangles to say that they are congruent. So once again, on this side it would look like angle side, but on this one it would be angle side angle. So you can't use that to prove that they're congruent. On part C, we have a right angle, so that's a start. That's good. We also have a hypotenuse on that right angle, which is 16, and so you can see this one's also 16. So that's good. And if this is 30, we know this is 60 degrees, and same thing on the other one, 30, 60. So it looks like we have an angle, a side, and then another angle. And same thing here, we have 30 degrees, an angle, a side, and then another angle. So by angle, side, angle, we can say that they're congruent. Since it is a 30, 60, 90 triangle, we could also use some of our shortcuts if we want to. If not, you can use your trig functions. If this is 30 degrees, then the short side, which would be right here and right here on this one, would be half of that, so that would be 8. And then this would be 8 here. The long side is the square root of 3 times the short side, so that would be 8 square roots of 3. And on this one, the interesting thing here is that this side right here is the long side, which is 8 square roots of 3. But we already know that this length right here is 8, so how do we find this value of x? Well, if the full distance is 8 square root of 3, then if it's 8 squared root of 3 minus the 8 right here, that should give us our value of x. Or you can say that x plus 8 is 8 squared root of 3. Either way, you're going to take 8 squared root of 3 minus 8. So you can leave that as your answer right here if you want to. If you want to approximate it, you're going to plug that in and you'll get approximately 5.9 units long for x. And here is the congruency. Now, you probably could have done that one a couple different ways. You probably could have also used angle side because we had all three angles as well. Part D, you have triangles built on top of them. This side length is the same as this one over here, so that's 5 and that's 5. We're looking for this angle up here, so we're looking for the value of x. We do have a right triangle again, so we have that. And so this length of this triangle right here, if you can see that, is going to be a length of 9. And then I'll try to show you on the other one here. This length for this triangle would be right here. So for this triangle would also have a length of 9. So that means we have a side length, the angle, which is the right angle, and another side length. So by side, angle, side, we know that they are congruent, which means that this value of x here and this value of x here should be the same. And we can use our trig ratios to do that. Let's see, we have the opposite and adjacent. We don't have the hypotenuse. So opposite and adjacent, we can use tangent. So we'll say tangent of x is equal to the opposite side, which would be a length of 9 over the adjacent side is 5. So you'll use your inverse of tangent of 9/5 to figure out what x is. So plug that into your calculator. Once again, you are using the inverse of tangent because you are looking for an angle measure. And so you will get approximately 61 degrees or 60.9 if you want to go that way. So we'll just say 60.9 degrees for the value of x. Question 12. Decide if the following statements are true or false. If a statement is false, provide a diagram of a counterexample. So let's go ahead and take a look here. Part A, all squares are rectangles. And that is a true statement. All squares are rectangles. Now the other way, all rectangles are squares, is not true. But all squares will have the 4 right angles as well. So we're good there, so that's true. And all their side lengths will be the same, but for rectangle that doesn't have to be, but for a square it is. So once again, that is true for all. All quadrilaterals are parallelograms. And that is false. Not all quadrilateral are parallelograms. We can build a quadrilateral as a counterexample here, and I'm just going to draw what that would look like. So there's a counterexample of a quadrilateral where it is not a parallelogram. Part C, all rhombi are parallelograms, and that is true. Once again, with a rhombi, the big thing is that all 4 sides are equal, similar to a square and a rectangle. So yes, that is true. It does hold all the properties of a parallelogram as well. All squares are rhombi. Once again, yeah, the most specific thing that you can have is a square. So not only is it a rhombi, but you also have it's a rectangle, it's a parallelogram. So yes, it's just that, once again, the square has the right angles where a rhombi doesn't. And then part E, the diagonals of a parallelogram bisect the angles. So the diagonals of a parallelogram bisect the angles. Is that true or false? And so it's true some of the time. It's not true all of the time. So we just need, in terms of the diagonals of a parallelogram bisecting the angles, that's true for a rhombus. So if we just draw in a parallelogram that's not a rhombus here, then the diagonals will not bisect the angles.